Right now, remember, we're talking about the analysis of two categorical variables. So today we're going to look at how to perform a hypothesis test for two-way tables or for that type of data. Always when you do a hypothesis test, your first step is to identify the population, so who or what group or the entire group you want to make an inference on. And then you'll identify the sample, so the people or group that's going to help you make that inference. Now, one thing that's unique for hypothesis testing for two-way tables or for two categorical variables, your null and alternative will not include a null value, so a number that you're hypothesizing about, because here we want to see if there's a relationship. So the null hypothesis, remember, is a statement of no difference or no relationship or nothing happening. So the null hypothesis would be that there is no relationship between the two variables. Now remember, the alternative is that there is something happening, or there is a relationship, or there is a difference. So here we would have there is a relationship between the two variables. Now you would be specific as to what the variables are, and it's an easy way to remember which is the null and which is the alternative. So the null, H sub O, there is no, and H sub A, there is a relationship. So that's how you can remember which is the null and which would be the alternative. So then in step 3, we're going to perform our testing. First, we would state our assumption in letter A. Here we're assuming the sampling distribution of the chi-squared statistic has a chi-squared distribution with degrees of freedom measured by number of rows minus 1 times number of columns minus 1. So if we think back to our example of the smoking and divorce contingency table, there were two options for smoking. So that means that our rows, we had 2 rows. So first we would have 2 minus 1. And then we had 2 options for divorce, yes and no. So that would be 2 columns. So we would have 2 minus 1 times 2 minus 1, or we would have 1 degree of freedom. So if you have a 2 by 2 table, you would always have 1 degree of freedom. So it's just the number of rows minus 1 times the number of columns minus 1. Now, conditions for this type of data, it is based on the expected counts. So it's explicitly based on expected counts. And this is important to remember because in a contingency table, you will have 2 counts in each cell. You will have an observed count, so what you saw in the data, and then expected counts, which is the calculation of what you would expect to see if the two variables were not related. So conditions here are based on those expected counts, and there's actually 2 parts to the conditions. First is that you can have less than 20% of cells with an expected count less than 5. So if you have a 2 by 2 table, there would be 4 cells, and so each cell would make up 25%. So in a 2 by 2 table, no cells could have an expected count less than 5. The second condition is that no expected counts can be less than 1. So less than 20% of cells can have an expected count less than 5, and no expected counts can be less than 1. If those things are true, then your conditions would be met, or in other words, you would be verifying the assumptions that you stated in letter A. To calculate your chi-squared test statistic, you are going to compare observed and expected counts for each cell. You will start by taking the observed count and subtracting from that the expected count. You will then square that difference, and then you will divide this value by the corresponding expected count. After you have done that for each cell, you will sum all of those values. So you will do the observed minus the expected for a given cell, squaring that difference, and then dividing by the expected count for that cell. After you have done that for each cell, you will then add all of those values up. So after testing, you're going to move to step 4, which is decision making. That will follow the same format as you've been using in the hypothesis test we've done up to this point. First, the test statistic distribution. So under the null, and because we calculated a chi-square statistic in step 3, we are using the chi-square distribution. Now, one thing that you'll notice about the chi-square test statistic is that it will always have to be positive. So because of that, you actually don't have the same look to your distribution as you did when you were looking at the normal distribution or the t-distribution. So we actually have a curve that isn't centered at 0, but it will actually start at 0. So it starts at 0, and then because of that, it has an odd right skew to it. So it'll kind of end up looking like that. Now there are different curves depending on their degrees of freedom, and we've already talked about how to measure that. When you calculate the chi-square, it does the same thing that the t and the z did. It gives you a location on your curve. So here we would have our chi-square locating us on the curve. So because of the nature of these problems, you're always looking for the probability of getting what you did or something more extreme. So the chi-square measures how different your observed counts are from what you would expect to see if there was no difference. So something more extreme than what you saw is going to always be the area to the right of chi-squared. So that means that every time we do these problems, we'll always be using chi-squared and then the area above it. Which means when you use your calculator, you'll be using the chi-squared CDF, and you will be finding the area from chi-square up to positive infinity. And you also will need to tell the calculator what degree of freedom you're using. And then finally, you make your decision the same way we have in the past. If you have a small p-value, meaning that it's less than alpha, we are going to reject the null. And if you have a p-value that's not small, we'll make the decision fail to reject the null. And then moving into step 5, we'll have the same scenarios. Had you rejected the null in step 4, you would have sufficient evidence for the alternative in step 5. And had you failed to reject in step 4, you would have insufficient evidence for the alternative in step 5. In the next few videos, we'll look at specific examples of how to calculate and perform this type of hypothesis.